Hi everybody, welcome back to another week of advanced methods for machine learning and data mining. We are in the middle of the high dimensional data chapter, and we talked about challenges of high dimensional data, the curse of dimensionality a lot 2 weeks ago. Last week we talked about supervised feature selection. There was the task where we try to get rid of features, but we keep original features, and typically we keep K features. Why do we want to get rid of them? Just recall, we want to get rid of redundant features because they may add biases and stuff like that, but at least especially we want to get rid of irrelevant features, and for that we had different ways to do that. We want to keep K original features, so that means if we have D original features, we want to get rid of D minus K. And we had different methods in this chapter 3 last week. This week we go a little bit a different way, feature reduction and metric learning. In that case, now we want to derive typically new features. So also with the overall aim, of course, to reduce dimensionality, but especially now we don't keep the original features typically, but we derive new features, and hopefully these new features describe, of course, the data set a little bit better, and we need less of them, obviously. So that is the basic idea, and especially if we think about redundant features, we may summarize them somehow. So that is where we can reduce them by deriving new features that summarize redundant original features. That's basically the idea. And we'll have a look at very different things here. Reference point embedding, which we'll start right now. Principal component analysis, which you probably already know, but let's have a closer look also on that. Singular value decomposition is a kind of extension or generalization of PCA. We'll have a short look at kernel PCA, because principal component analysis and SPD only can capture linear correlations, and if you have non-linear correlations, you can, for example, apply kernel PCA. We'll see how that works a little bit. And we also talk a little bit about further measures very briefly, because this field of feature reduction is very, very large, and this is just a snapshot here on hopefully one of the most important, or at least most well-known things. Once again, all of those things are sometimes supervised or unsupervised, but in any case, again, they have some specific assumption, and you have to be clear about the assumption. That is, for me, very important, that this is your takeaway of all of those methods, that you know what kind of assumptions are behind those methods, because that gives you, again, an idea about how to actually interpret the results of the whole data science process. Recall, the whole thing is a process, not only the machine learning application or the application of a machine learning model, but this is pre-processing, and you can do a lot of things wrong in pre-processing. The buzzword here is, of course, shit in, shit out. Okay, so let's jump in to this fourth subsection, and we start with some basic ideas first, and then have a look at the reference point embedding. So once again, as I said before, instead of removing features, we now try to find a lower dimensional feature space, generating, modeling the original feature space as accurate as possible. So we want to have lower dimensional feature space, but the original features are typically not kept, but we derive new ones that hopefully, that is this as accurate as possible, hopefully represent the original data as good as possible. Meaning that, for example, we want to summarize redundant features. Irrelevant features may also be somehow summarized, but they should be weighted by small values or even erased, in the best case, of course. So the new features may be some combinations of the old ones, and in that case we want to, of course, somehow summarize the redundant features and weight the irrelevant features very, very low. Yeah, so that is the basic idea. Yeah. And yeah, some sample methods among lots of others. I told you that this is a very broad field, so we will have a look at reference point embedding, which is unsupervised. PCA is also unsupervised. Singular value decomposition is unsupervised. SVD sometimes gives you even more than just feature reduction, but also a first kind of partitioning. So SVD can sometimes also give you some idea about the natural grouping, kind of clustering. Yeah, it's not really a clustering method, but we will have a look at that. And then we will have two supervised measures, which is Fisher phases and a very close sibling, so to say, is relevant component analysis, and last not least, large margin nearest neighbor method. Yeah, so that you just see that it's not only supervised or not only unsupervised, but we can also do that in a supervised fashion. But let's start with the reference point embedding. So first of all, so the task now is that we describe the data with fewer features. We reduce the number of columns and also come up with different columns, with probably summarizations or combinations of the original columns. And we have to be clear that, like in feature selection, of course, there will always be an information loss. Yeah? And of course, and that is the point here with as accurate as possible, we would like to somehow describe the original data with the original features as best as possible in this new derived feature space. Yeah? And I already mentioned supervised and unsupervised methods are out there for doing the job. So now, really, let's jump into the reference point embedding. So the idea is very simple. We describe the position of each object by their distances to a set of reference points. Yeah, so that means we just define some reference points, sometimes it's also called landmarks, and then we just compute for each point, for each observation in our data set, for each feature vector, we compute the distance to all the reference points, to all the landmarks. Yeah? So given a feature space, which is n-dimensional in that case, with n features. Sorry, the terminology, I just see that the terminology is not really consistent, but okay, let's keep it like this here first of all. So we have n features in that case. D1 to dn are the original features, and the target is a k-dimensional subspace or space, not subspace of this one, because we want to derive new features, which yields an optimal solution for the given data mining task, of course. Yeah, and now, as I said before, we have given a set of reference points, landmarks, k in that case, because we target a k-dimensional space. So we work with k reference points and this in a distance measure, and we transform each original vector as follows. We just record the distances of this vector to all the reference points, as you see here. Yeah, and then these distances are our new features. Yeah, so we reduce or derive a new feature space, and the new features are represent the distances of the particular point to the corresponding reference node or reference point, to the corresponding landmark. So you see here, the first feature is the distance, the first new feature of x is the distance of x to the reference point, to the first reference point, of course, in the original feature space. Yeah. The second one is the distance to the second reference point, and so on and so on. And since we have k reference points, this ends up in a k-dimensional representation for the original d-dimensional point x. Yeah? There's a kind of visualization here. So if we have these different reference points here, then if we have r here, r1 here is our reference point, which is the origin in that case here. All these points here are transferred into the distance to this reference point here. So all these guys, the white guys here, get some closer distances, some smaller distances, and those 3 points here get higher distances here. Yeah? The choice of the reference point, of course, somehow has an impact on the final representation in that case. Yeah? So we get from a two-dimensional space here into a one-dimensional space, and this new feature here is somehow independent, not really independent, of course, but has nothing to do with the original features, first of all, on the first glance, yeah? But with the distance in this original feature space to the reference point. Yeah, so that's it already. So a discussion, the distance measure, of course, is usually determined by the application. Yeah, recall about feature transformation, similarity measures, and stuff like that. Selection of reference points can be important, as I just said. Yeah, very often we try to use, for example, centroids of cluster classes if we are in a supervised setting, or cluster centroids if we have an unsupervised setting, and we use k-means to detect k cluster centroids as reference points. Points on the margin of the data space can also sometimes be interesting, but think about these marginal effects of the cursive dimensionality, so be a little bit careful about that. Very often people just use random samples. Yeah? Reference the choice can be quite tricky sometimes. Yeah, it's a very simple approach and easy to implement, so that is absolutely on the plus. The transformed vectors yield upper and lower bounds of the exact distances in the original feature space. Yeah, you may ask, what the hell is that good for? Good question. Well, that is typically interesting if the distance measure is a metric, meaning that we have the triangle inequality, and then upper and lower bounds can be used for speeding up distance computations and clusterings and stuff like that. So that is the point for why people make a big ado about metric spaces and metric distance functions. So in that case, that could be a good asset here. Yeah, but in most cases, forget about it. However, there are some downsides. So even using d-reference points does not reproduce the d-dimensional feature space. Yeah? So if you have a d-dimensional feature space as the original feature space, using d-reference points does not mean that we get the same feature space as before. Yeah? Which is sometimes maybe a little bit unintuitive, but that's how it is. And the selection, as I said before, is important. So selecting good reference points can be extremely important, but can be also very difficult. Yeah, so that is, as I said before, the downside of this method. Yeah, so that was reference point embedding.